having Monday be the problem session rather than Friday be the problem session. So anyways, I'll definitely have a lecture on Wednesday. And so at that point, I'll let you know, but it would not be too soon to, start working on, some exercises. So again, as usual, or as per new usual, the ELC page contains a list of exercises. Most of the exercises that I stuck there either came up in the last lecture or will come up in this lecture. And then I think I just decided to, I just included a couple of exercises on like the Kroll topology on an infinite Galois extension. And so the relationship between Galois groups and profinite groups, which surely will be, at the center of the sort of thing that we want to talk about as soon as we start talking about Galois homology. Yeah, so one exercise is to prove that every profinite group, so a profinite group, one exercise, I guess, is to show that a topological group is compact, which includes Hausdorff, and totally disconnected, if and only if it is an inverse limit of finite discrete groups. Okay, so that's just in the category of topological groups. Those are equivalent conditions on a profinite group. And then a relatively easy exercise is to show that every on the automorphism group of any algebraic Galois extension, even if it's infinite, there's a natural topology called the Kroll topology, which is easy to see, makes it into a profinite group, and in particular because the automorphism group of an infinite algebraic Galois extension can be naturally viewed as an inverse limit of finite groups. So there you go. So that's one direction. And then the other direction is that, in fact, every profinite group is isomorphic as a topological group to the Galois group of some Galois extension of fields equipped with the Kroll topology. Okay. This was maybe the first theorem that I ever proved, like, myself. I think I came up with this sometime around my second year in graduate school, and then later I realized that, like, I don't know, at least 2 or 3 different people had written papers, short papers, proving this result. So I think it's sometimes called the Lepton-Waterhouse theorem, because these are 2 people who wrote papers that every profinite group is a Galois group. Not over Q. You have to pick both the top and the bottom field extensions in order to do it. Okay, so that's a fun exercise. I'm sure there's many different ways to do it. Yeah, any other questions about course stuff? No? Seems kind of straightforward. Any content questions? All right, well, we can get back into it. So again, I really, famous last words, but I really do mean to be following the course text pretty closely. I'm not really doing it yet though, because I wanna just do a little bit of cohomology and also it's just to show you what it is, homology of arbitrary groups, not necessarily finite groups. I mean, that's important in certain branches of mathematics. Group homology and group cohomology is interesting. It actually has interesting applications in topology in particular, but also I think you just you want to know when you're using the finiteness of your group, I think, in order to get a clearer understanding. Okay, so let's see. So as a brief review of the first lecture, we introduced the category of G modules for an arbitrary group G. This is just Z modules, which admit as an action of the group G by Z-linear automorphisms. And I stated without proof, the proof will come in this lecture, that the category of left G modules is an abelian category with enough projectives and enough injectives. And therefore, whenever you meet a right exact functor, you have left derived functors and a corresponding what do you call it? They form a homological delta functor, and you get a sequence of homology groups. And whenever you have a left exact functor, you have corresponding right exact functors, which form a cohomological delta functor, and then you get a long exact, you have these cohomology groups, and you get a long exact sequence in cohomology. And then the 2 examples, the one example that we had of a half exact functor, so taking the invariance, so the largest, if you have a G module, the functor which associates the largest submodule on which the group acts trivially, It's literally just the submodule of elements on which every element of the group X has the identity. That's M super G. That's called the module of invariance, and that's the really straightforward exercise is that that's a left exact functor. I gave you an example to show that it's not exact, and so then we can take cohomology groups, and those are our group cohomology groups. We can come at it in other ways, but that's the first way. And then the other way around, if you, instead of taking the largest invariant submodule, you can also take the largest invariant quotient. And if you stop and think even for a little while, you clearly need to impose the relations that gx is equal to x for all g and g and for all x and m in order to get an invariant quotient. I guess it's a one-line exercise to see that the z submodule generated by this is actually stable under the action of the group, and therefore this is a sub G module, and then the quotient is pretty manifestly the largest invariant quotient. And then the corresponding exercise is that taking the covariance, as we call it, is right exact, and I gave an example to show that it's not generally exact. And so therefore you get left-derived functors by taking a projective resolution. Previously, we were supposed to take an injective resolution, and then you take you take your projective resolution, you strip away the m, you apply the functor, and then you take the homology of that functor, just kernel mod image, and those are the group homology groups. Okay. Yeah. So by the way, maybe I should say a really nice reference for group cohomology and a little bit of group homology in general is this Springer GTM, I believe it's just called Cohomology of Groups by Kenneth Brown. So this is kind of been a standard reference for me for many years. It's a nice, I enjoy it. If you look in that book, then you'll see how directly inspired I am by some of the stuff that he does. But so he has some nice connections to topology in particular. I mean, since I've come this far, maybe I'll just throw it out into space. So among other things, so if you have any group, you can define in algebraic topology, one defines what's called, maybe I should write this down, what's called the Eilenberg-MacLane space of that group. And so that's a thing. Let me say just a few words about it. I think there's a brief treatment of this at the end of my homological algebra notes, which are on, I mean, you can Google for them, they're on my exposition page. So I guess for some reason, usually we denote this thing by, most topologists call this pi. So let pi be a group. Already don't feel like a number theorist, but let pi be a group. And so then there's a what's called an Eilenberg-MacLane space. So this, let's see, so it's called a k-pi1 space. So what is this? An Eilenberg-MacLane space is a space X. Let's see, I'm just going just straight from my memory here, so let's see how it goes. So this is a CW complex. Let's see, it's connected. Its fundamental group at some base point is the group that you're started with, and all the higher homotopy groups are trivial. And in fact, that some of that last stuff, so that implies that if I take the universal cover, okay, so this is going to be a pi Galois covering space, right? And so this other stuff implies that this universal cover is going to be contractible. And among other things, this is some kind of universal space for pi bundles, if you fiber bundles with. Anyway, too much. Okay, so this is an important space. Okay, and let's see. So that's just there exists such a space, and so what am I trying to say? So this is unique up to homotopy equivalence. It couldn't. I mean, everything I'm saying is a homotopy is invariant under homotopy equivalence, so it couldn't possibly be any more unique than that. And I think just by some standard Whitehead type theorems in algebraic topology gives you that this is unique. Anyway, has anyone ever seen this before? Maybe I should stop and ask. No? I guess we don't do it. We only do like we don't have like a real algebraic topology class at UGA, right? We have the basic qual level course, and if you don't get to cohomology in the qual level course, you're not going to get to Eilenberg-MacLane spaces. So that's a bit of a shame. I was an undergraduate at the University of Chicago. Algebraic topology is very popular over there. So anyway, I think I learned about this in my one algebraic topology class. Graduate level. All right, so right, and so what's the point? The point is that you can take homology and cohomology groups, of course. And so if I take, I'll just do a star as the topologists do. So the, let's see. Maybe I'll do x pi just to indicate the dependence on pi. So the homology groups of your Eilenberg-MacLane space, just with regular old integer coefficients, are naturally isomorphic to the group homology with coefficients in Z. So again, standard convention, when you're doing group homology or group cohomology, if I just write Z and I'm supposed to write if it's supposed to be a G module and I write Z, I mean the additive group Z with trivial action, okay? And similarly, the cohomology of the Eilenberg-MacLane space is the group cohomology with integer coefficients. And among other things, so then you kind of, I mean, one thing is you might want to generalize this. So then you might want to say, so what if I actually take a G module M? Okay. And so what if I actually took, again, I just defined the group homology, right? And so now, what here, the group homology just of where M equals Z corresponded to the homology of the Eilenberg-MacLane space with integer coefficients. So this kind of raises the question of a topological interpretation of the group homology. And so I'm just gonna write something down. I'm not gonna explain it. So there's a notion of like a local system on a topological space where so M is some corresponding local system. And so I'm just saying there is something in topology, something which is, you could interpret it. The topologists don't necessarily think of it this way, but you could interpret it in some sheafy way if you wanted to. You could interpret this as some type of sheaf, and then again, the group homology, arbitrary group homology, is going to be some kind of topological cohomology of some corresponding local system on the Eilenberg-MacLane space. So what I'm saying is that, in fact, in full generality, group homology and group cohomology are actually homology and cohomology of an honest topological space. Okay, so I mean, as homology goes, I mean, there's all kinds of things, in homological algebra where you take derived functors and you call it homology or cohomology, but there really is like a topological space here. Okay. That is not going to be very important for what we're doing, but it's kind of anyway, sort of inspirational. All right, and again, I think in my homological algebra notes, I at least define Eilenberg-MacLane spaces, and I say just a little bit about it. All right, any questions about that? No. Okay, so let's go on. So the main thing to introduce in this lecture in order to kind of tame them, we made the definition, but like unfortunately the abstract definition of homology or cohomology in terms of derived functors on a billion categories, it's a very general definition, but it doesn't. There's very little that sort of becomes clear in any concrete sense from that definition. It's just so formal. Like how do you actually compute, any of these things? Like are we really supposed to write down every time I see a G module, I'm supposed to write down a projective resolution of it, and then I'm supposed to write down an injective resolution of it? Like that sounds like a lot of work. So no, we don't have to do that. And so, right, so the thing which really, and then another question is, I told you that this was an abelian category that has enough projectives and enough injectives. I didn't tell you why, and so here's why. So I actually rewatched most of the first lecture, and I did everything but tell you why in the first lecture. Okay, so the group ring is the answer. So let me just remind you what the group ring is in slightly more generality for any monoid. Okay, so set with a associative binary operation having an identity element, doesn't have to be commutative, that's a monoid. Let R be a ring, doesn't have to be commutative. Then we have the monoid ring R bracket M. Okay. So first of all, this is a free left R module whose basis is just formally in bijection with the elements of M. So we may forget about these brackets. At some point, we're probably going to forget about the brackets, but initially it's helpful to write bracket M as the basis in the group ring. Okay, so this is just a direct sum of copies of R indexed by the elements of M. So that's an R module. And what's the multiplication? Well, these are formal R linear combinations. And so, I really just need to know how to multiply two basis elements, and then everything else will kind of follow just by distributivity or by linearity, however you want to say it. And so, well, how should I multiply two basis elements? Well, I'm in a monoid, so I should multiply them using the monoid operation. Okay, so this is the monoid ring. And I introduced this in my commutative algebra class, for instance. So it's a very basic object. And let me just kind of remind you of the universal property of monoid rings. Let's see. So I guess there's several ways to formulate this. So here, I'm going to assume I'm only interested in the monoid ring in the case where this R is actually a commutative ring. Okay, so the monoid ring will be commutative, I guess, assuming that R and M are both non-zero. Then the monoid ring will be commutative if and only if both R and M are commutative. Okay, but I'm only interested in the case where R, the ring, is commutative, M need not be. In that case, for all R algebras B, okay, I like the idea of an R algebra a little bit better if R is commutative. For all R algebras B, there's a natural isomorphism between the set or group, I guess, of commutative group of R algebra homomorphisms from the group ring into any R algebra. So in other words, what do I need to do to define an R algebra homomorphism from my group ring with coefficient ring R into B? All I need to do is take a monoid homomorphism from M into the multiplicative monoid of B. So that's the universal property. So that's a standard exercise. And so the next thing to do is to specialize R to be Z and M to be G, an arbitrary group. And then you don't need to use this, you could see it in some other way, but you could see it from the exercise that every left G module canonically has the structure of a left module over the group ring. Okay. How do you see this from the universal property? The module, the Z algebra, otherwise known as ring. So the ring B that you want to take is not, well, anyway, it's the endomorphism ring of M, okay, which is a not necessarily commutative Z algebra. And so then from this, we see that a homomorphism from ZG into NZ of M is going to be the same as giving a homomorphism from the group into the multiplicative group of this ring. Okay, and then if you unwind that definition, then what am I saying? On the one hand, just think about that for a second. Yeah, so if you unwind that, then over here, you're actually getting a ZG module structure, and over here, you're getting a G module structure. Okay. You don't have to do it this way. You can, so anyway, but so the claim is that the notion of left G module is kind of manifestly the same as the notion of left ZG module. Okay, if you have an action of G on your commutative group by Z-linear isomorphisms, then you can immediately extend that to an action of ZG, because every element of G acts however that element of G acted before, and the Z-linearity of the action is necessary and sufficient in order for that to define it. Okay, I'm just saying it in a different way. Anyway, so you should either using this exercise or in whatever manner seems best to you, you should convince yourself that there's a kind of obvious categorical equivalence between left G modules and left ZG modules. Okay. Right. And so, right, so it's kind of amazing how much order and simplification, pun not really intended, comes from consideration of group rings. And so let's try it. So yeah, so let's just get into a couple basic exercises here. Yeah, so group rings are just kind of wonderful objects in general. I was looking. There's a recent paper that does some work on like Chevalier-Varning type stuff, which I then kind of used over the summer and adapted to my own work. And they just introduced group rings and augmentation ideals and all this stuff. And I was like, what the heck do group rings have to do with any of this? And like, at worst, it's a really lovely kind of bookkeeping device. And so anyway, group rings are your friend. So just a couple exercises. If G is a finite group, I can define a norm element. Okay, that's what this is called. What is it? It's just the sum over all of the elements of the group. Okay. No, again, the group needs to be finite in order to make this definition, because these are, formal finite Z-linear combinations. Okay. So I have such an element, and what's the point of this element? Well, this is kind of the usual trick. If you want something to be invariant under the action of a group and it isn't, if you can sum or average over all of the elements of a group, then something will have to be invariant. If your group is infinite, then how do you average over the elements of the group? Hopefully there's some kind of integral somewhere that would help you do that. But if your group is finite, you can just sum over everything, right? And so it's completely obvious that this norm element is G invariant, right? Because if I hit it with any element of G, that just permutes all the G's. The exercise is that, that this is giving you all the G invariants in the group ring itself. Okay, so of course, ZG modules correspond to G modules, and so therefore the group ring itself is kind of our favorite G module. Okay, so free rank 1 ZG module. Okay, and so the exercise is, first of all, that the Z submodule generated by the norm element is the same as the ZG submodule generated by the norm element. That's pretty easy, because after all, N is G invariant. And anyway, and then moreover, literally just the collection of, this is a ring of characteristic 0. And so it's, you have this element and just all the integer multiples of this element. So that is, they're pretty clearly G invariant. And the exercise, which is not so hard, is to show that these are all the G invariant elements. Okay, so that's what happens if G is finite. What if G is infinite? Well, I don't have a norm element and I don't have any invariance either. Okay, so show that if G is infinite, then if you're being invariant under an infinite group is kind of stronger than being invariant under a finite group, roughly, right? And so it turns out that the module of G invariance of the group ring is just 0. Okay, so very basic exercise. All right, what else? Using the universal property of the group ring, for instance, we get an augmentation homomorphism or augmentation map. This is a ring homomorphism from the group ring into Z. So again, what does the universal property say? The universal property says, if here I'm going to take R equals Z. So to give me a Z algebra, a ring homomorphism from the group ring into any ring whatsoever, you just have to give me a map from G into the multiplicative monoid of Z, okay, multiplicative, not additive. Okay, and so what's my map going to be? It's going to be kind of the trivial map in the sense that the identity of the multiplicative monoid of Z is 1, not 0, but 1. And so I'm going to map every single element of G to 1. okay? And that's clearly a multiplicative homomorphism. So it's sort of like evaluating each element of the group at one is how you can think about it, okay? And so, right, and so so by the universal property, there's a unique homomorphism which maps every group element to one, and therefore an arbitrary group element looks like this, and therefore, yeah, it really looks like you're evaluating each group element, you're setting each group element equal to one, and so it takes this thing to just the sum of the coefficients. So that's the augmentation homomorphism. Okay, very important homomorphism. So it's a homomorphism of rings, so its kernel is a two-sided ideal. So by definition, I, the augmentation ideal, is the kernel of the augmentation map. So what is this? This is just the collection of all finite z-linear combinations of elements of the group so that the sum of all the coefficients is equal to 0. Okay, so kind of no problem there. And then, well, you know, just like for any homomorphism of rings, we get a short exact sequence of ZG modules. Okay, this is just an ideal. That was, okay, that triangle is subtly, anyway, it's an ideal. All right, here again, we think of Z as having the trivial G action, okay, which is good. So I guess what I'm saying is maybe I'm saying a little something here. So if you take this short exact sequence of rings and put the trivial G action on Z, then this is a short exact sequence of G modules. Z equivalently ZG modules. So here I is also a little exercise. I is a free Z module whose basis is with a basis given by the collection of elements G minus 1, where G ranges over all non-trivial elements of G. Maybe I'm writing later. I'll write E maybe for the identity of G. So E is equal to the identity in G. Okay. And so of course, so here by bullet, I mean, take out the identity. So if G was equal to the identity, then this would give me 0. So I don't need that as part of the basis. And so yeah, just a little exercise. The augmentation ideal is a free Z module generated by these guys. It may or may not be a free ZG module. That's a different thing. Okay, let's see. So there is a really trivial case here where, so if the group is trivial, then the group ring is just Z itself. And then you can see from this, if not otherwise, that the augmentation ideal is just 0, and the augmentation homomorphism is just the identity map. That's quite a trivial case. So just you know, not the most profound remark in the world. ZG modules where G is the trivial group are just Z modules. But, okay. So next proposition is, so I claim that this short exact sequence only splits in the trivial case when the group is trivial. Yeah, gosh, I can't. Doesn't really matter, but I guess I'm using E for the identity of my group. Okay. And so I just told you that it definitely, if G is the trivial group, then this sequence is 0 to 0 to Z to Z to 0. So that definitely splits. So what about the other direction? So basically, I'm saying that I never have a section here, you know, as a ZG module section when the group is non-trivial, right? So let's see why. So if I did have such a section, let's just write it in. Do I have a section? Well, where does 1 go? Right, so Z has the trivial action, and so if this is a G homomorphism, then sigma of 1 has to go to a G invariant element, right? And it has to go to a G invariant element that under the augmentation map maps back down to 1. Okay, and if we just analyze that, then already we can see that that's not possible. First of all, if the group is infinite, well, I just said there are no G invariant elements other than 0. 0 is going to map to 0. It's not going to map to 1. And then if the group is finite, then it would have to be a multiple of the norm element. But the norm element, if I hit it with the augmentation homomorphism, the norm element itself is the sum of all the elements in the group. So under the augmentation map, it's going to map to the order of the group. And so therefore, any multiple of therefore the image of the augmentation, the image of the Z module generated by the norm element is going to be order of G inside of Z, but if G is finite and non-trivial, its order is bigger than 1. And so, yeah, so you see that there is no G invariant element over here that maps to 1 under the augmentation. Okay. So therefore, this sequence never splits. Who cares? Well, we do. So that tells us something. So what did we just learn here? We just learned in particular that if the group is non-trivial, then Z with its trivial G action is not a projective module. Can we, you can only argue with this if you don't remember what a projective module is. I mean, so a projective module means a projective object in any abelian category means, you can re-express it in several ways maybe, but it certainly means that if you have a short exact sequence with last term equal to your guy, then the sequence splits and the sequence doesn't split. Okay, so Z is not a projective ZG module. Okay. Right. And so now let me make an aside here. So things would work better in a slightly different context, which is closer to classical representation theory. So instead of working with ZG modules, what if I worked with KG modules where K is a field? Okay. And now I just showed you that things don't work so well when the group is infinite. But anyway, for what I'm going to say right now, yeah, so I guess I didn't really think this through. Presumably, yeah, so presumably, what am I not saying here? So if I look at KG modules over any field K, and when the group G is infinite, presumably the exact same argument will show you that Z is again not a projective KG module. Okay, so maybe I'll write that down somewhere. So so show if K is a field and G is an infinite group, then again, as totally as before, we have this augmentation map, no problem. The augmentation map kind of began its life in representation theory, in fact. Exact same map. You take every group element and you send it to 1. So then K. So then the sequence does not split. Again, really for exactly the same reasons, and therefore K with trivial G action is not a projective KG module. Okay, so this is sort of explaining a sense in which representation theory for infinite groups does not work as well as representation theory for finite groups. Okay, so now let me come back to the aside. I made an aside for my side. So suppose I have a field and I have a finite group. So I just want to remind you, there's this really classical theorem. I'm sort of confused by this because representation theory is really popular at UGA, but you'd think that we'd have a standard course where you learn this stuff, and maybe you do. So can anyone tell, who's seen this theorem of Majka before? What course have you seen it in?
Seminars.
Seminars.
Same.
I see. Okay.
Like
All right.
Sydney.
That works. Yeah, so no, when I learned this when I was an undergraduate in some algebra course. Anyway, so there's this nice theorem of Majka. So Majka's theorem says that the following are equivalent if you take the group ring with coefficients in a field for a finite group G. The group ring is semi-simple. What does that mean? That has a lot of equivalent characterizations, but among other things, it means that a ring is semi-simple if every short exact sequence for modules over that ring splits. So equivalently, if every left module over that ring is projective, equivalently, if every left module over that ring is injective, okay, and then you say that Anyway, yeah, so that's what it means for a module to be semi-simple. And so the group ring with field coefficients in a finite group is going to be semi-simple if and only if the characteristic of K does not divide the order of G. And okay, what does that mean? So in particular, if the characteristic is 0, 0 only divides 0. Okay, so the classical, probably what Mashka actually proved like around the turn of the century. I think he was a young mathematician at the University of Chicago. Probably what he actually proved is that the group ring for a finite group with complex coefficients was semi-simple. Anyway, so that's the result. So what's the point though? The point is that if you assume both of those things, let's say you're working over a field of characteristic 0, then all of a sudden the group ring is semi-simple, so everything is projective. And what does that mean? That means in particular that there is no non-trivial cohomology theory. This if you track this through, this is going to, oh, I guess I'm gonna, okay, now I'm actually kind of getting ahead of myself a little bit, but at least if you get to the end of this lecture, this is gonna mean that if you took homology and cohomology groups of a finite group with coefficients in a field of characteristic 0, or more generally not dividing the order of the group, then all of the higher homology and cohomology groups would vanish. Okay, so there's something in classical representation theory which is much simpler than that. It's too simple to have these non-trivial cohomology groups. And now is when I remind you, back in the first lecture, right? In the first lecture, I gave you this example where I was working with, I didn't just have groups, I had R vector spaces, right? And I made this point, now you see why I said it. The group here, this was an example of a, I had a short exact sequence of G modules, and I took its G invariance, and it was, and I did not get an exact sequence. And I'm saying that if I took a finite group and I took R vector spaces, then no, the functor would be exact, but notice this is an infinite group. Okay, so there's something, the very, very, very classical classical representation theory of finite groups on vector spaces in characteristic 0 is so nice that there's just no cohomology whatsoever. On the other hand, if I were doing modular representation theory, so if the group is finite, but the group has order divisible by P, and I work over a field of a characteristic divisible by P, if you open up any representation theory book, that's called modular representation theory. That's much more in the spirit of what people around here do. Some people anyway, Dan Nakano, Brian Bowe. Modular representation theory is so much more complicated than classical representation theory. Again, precisely because of the fact that in the one case, every KG module is projective and injective, and in the other case it isn't. Okay, so let's see. But now let's finally make the point. Because a G module is exactly the same thing as a left ZG module, well, then the category of G modules is as an additive category, the same as the category of ZG modules. And therefore, like this is the answer, as for the category of left modules over any ring whatsoever, this ensures that the category of G modules is an abelian category with enough projectives and enough injectives. Okay, so that's why. Okay, so that's the key point. All right. Let's see. Yeah. So now I want to explain what it's so right. So that explains why we can take projective resolutions and injective resolutions, but if we use a little bit more algebra, then we can reinterpret our derived functors of invariance and co-invariance as literally the type of derived functors that you study when you study modules over a ring. So in fact, I'll spoil it a little bit. I'm just going to come down later on the page, I guess. So I claim that among other things, group homology is some kind of Tor over the group ring, and group cohomology is some kind of X over the group ring, which has got to be good news because there's all these nice facts telling us about Tor and X. Okay, so that's what I'm going for. So the key proposition is that this is what makes this work. So the invariants are Hom over the group ring from Z into M. Okay, so here these things get tricky. So here this type of Hom, I only mean it as a Z module, okay, which is good because I only mean MG as a Z module, but you need to sort of say this. So that's the first thing. And then the second thing is that the co-invariants come down to this type of tensor product. And now you see the non-commutative tensor product, and you sort of check it out a little bit here. So what am I doing? This is just Z with trivial G action, so I can do whatever I want, but evidently I'm viewing it as a right ZG module with trivial action. So okay, I can do that. And then M I'm still viewing as a left ZG module, and therefore it's a right Z module. And again, I do this kind of matrix multiplication, like canceling out, and I get, if I do this type of non-commutative tensor product, then in the end I get a ZZ bimodule, which is just a Z module. Okay, so this is the claim, that the invariants come out as a Hom over the group ring and the co-invariants come out as a tensor. This is not hard at all, so let's see why this is true. So what are the G homomorphisms from Z into a G module M? Well, of course, first of all, it has to be a Z homomorphism, and this is a free Z module. So if you just, the Z homomorphisms would just be, you take one to whatever element of M you want, so they would correspond to the elements of M. But then I also want the map to be equivariant with respect to the G action, but the G action here is trivial. So since G of, so here's the tiny little calculation. So phi of 1 is phi of G times 1 because Z has the trivial action, and that should be equal to G times phi of 1. And so evidently phi of 1 had better be a G invariant element. And then the converse is also true. So if for any G invariant element over here, if I send 1 to that G invariant element, and I send n to n times that G invariant element, you check immediately that that gives you a ZG module homomorphism from Z into M, and that's the proof. So the ZG module homomorphisms from Z into M are naturally in bijection with the G invariant elements of M. That's what I said. Okay, what about part B? It's pretty easy, but thank goodness we introduced the augmentation ideal. So MG is this quotient. It's M mod that guy. Now you look at this a little bit and you say, huh, gx minus x, that's like g minus 1 acting on x. Oh, that's the image of x under g minus 1, which is an element of the augmentation ideal. I just said that the augmentation ideal is generated by all of the guys of the form bracket g minus bracket of 1. And so you think about that for a little bit, you quickly convince yourself that this G submodule that we're quotienting out by is precisely the image of the augmentation ideal acting on it. That's just exactly what the augmentation ideal is. It's formal Z-linear combinations of G minus 1. And that's what we're doing. We're taking G minus 1 applied to elements, and we're taking Z-linear combinations. Okay, I'll do a sub Z here. Okay, so that's helpful. So therefore, the co-invariants are in fact obtained, if you like, by tensoring from ZG to ZG mod I. Okay, so that's exactly what I'm going to do. I'm going to take M and I'm going to tensor it from ZG to ZG mod I. Again, it's a non-commutative tensor product, so you stop and convince yourself that everything, everything matches up here. Okay. Let's see. But we know what ZG mod I is. What is ZG mod I?
It's just C as you have there.
Yeah, so it's written, but the reason is that Well, I was the
exact
kernel
sequence.
of the augmentation map. So guess what? Guess what the ring modulo of the kernel is? It's the image, which is Z. Okay, so Z with a trivial Z module structure, and there you go. Okay, so the covariants are M tensored over the group ring, with Z. Okay, awesome. So what does that mean though? If you just rewrite that, that means that the invariants as a functor are a Hom functor from Z into blank. And the co-invariants as a functor are the tensor over the group ring with Z. Okay, and therefore, now you go back and you look at these things, and so you see that again the tensor. Okay, these are both Hom and what do you call it? Hom and tensor product are both bifunctors, meaning they take two arguments. For the tensor product, it doesn't matter because A tensor B is isomorphic, naturally isomorphic to B tensor A. So that's pretty clear. So maybe I should do the second one first. So again, the derived functors of tensor with something over a ring are Tor, Tor of the thing that you tensor with. So it must be the case that the homology groups are, the nth homology group is the nth Tor functor of Z with M. The other way around, again, the X is not commutative in the two variables. It matters a little bit, but yes, it's true that the derived functor, if you take again, it matters which which one I'm fixing and which one is invariant. So this one where I fix the first one and blank out the second one, first of all, that's a covariant functor, whereas the other way around would be a contravariant functor. You just have to kind of write it down or think about it a little bit every time. So this one really is a left exact functor in general, okay, and is exact if and only if the module is injective, unless I'm mistaken. Anyway, so right, so that's the answer. So we're taking derived functors of the Hom, okay, and so therefore the nth cohomology group is, among other things, equal to X over the group ring of Z with M. Okay, so that's, there's no proof if you know what the Tor and the X are, then that's just exactly what they are. Okay, so that's an extremely important result. And again, now the kind of bifunctoriality of the Tor and X can be used to our advantage here. So backing up a little bit, for any ring, if I take Tor AB over that ring, in order to compute the Tor functor, I kind of have my choice. I won't go through the whole thing, but I can either, I can sort of, the idea is like I can sort of fix one and I can view it as a functor of the other, or I can have it the other way around. And they behave symmetrically in the case of Tor. So if I want to compute the Tor functors of AB, I can either use a projective resolution of A, and then tensor B with that and take the homology, or I can take a projective resolution of B and tensor A with that and take the homology, right? So I have a choice here. It's a more symmetric choice than it's going to be over here, but I still have a choice. And so if you think about it, which one would I rather do you think? Would I rather take a projective resolution in the category of ZG modules of M, or would I rather take a projective resolution of Z? Well, I insist that somebody say something, or I won't go to.
Just do it once for Z.
Yeah, so if I do it for M, then first of all, Z with that doesn't really scare me that much. Z with a trivial Z module structure, right? That's got to be a simpler module than some totally arbitrary ZG module. And again, as Freddie says, well, the thing that was, one of the things that was dismaying is that a priori, in the last lecture, it seemed that for each and every G module M, I had to do some resolution separately depending on M, and absolutely I do not. If I just take a projective resolution of Z, then I can tensor that projective resolution with M, then take the homology. So I do that kind of once and for all. So only one, for each group, I only have to do one resolution. Now let's go over to the other one. The X groups are a bit more interesting. Again, you just can look this back up as I'm sure I looked this up before I wrote this down. So to compute the X groups, you can either use a projective resolution of A, or you can use an injective resolution of B. Okay, this goes under I think this goes under the heading balancing X. Okay, so you can have it either way. Well, which again, so in our case, you go back and you say, well, would I rather take a projective resolution of Z, or would I rather take an injective resolution of M? Kind of sounds like the same answer, right? And you notice that both ways, I decided I would rather take a projective resolution of Z. So in fact, if I take a projective, and again, I can just take a free resolution of Z, right? And so what you see is that one projective resolution, in particular, one free resolution of Z over the group ring will compute both of these functors at the same time. Okay. So yeah, so in our case, we see that we can use a projective resolution of Z over the group ring to compute both the group cohomology and the group cohomology at the same time. So that seems to be preferable. Okay. And it turns out that this is going to come up in the following lecture. There is a standard projective, in fact, free. There is a standard free resolution of Z over the group ring. I will show you what it is. And then if you take the homology, you use that to compute the group homology, and that gives you the standard description of group homology in terms of chains and boundaries. And then you use that standard projective resolution, and you use that to compute group cohomology, and that gives you the standard description of the group cohomology in terms of cochains and coboundaries. Okay, so we'll do that. We'll do that next time. I think I'm going to go maybe just for 5 more minutes here. Well, yeah, maybe the proof of the anyway. The statement. I just want to work with these definitions a little bit. So for any group G, I'm going to compute a first homology. Okay, so secretly, among other things, this is literally the first homology group in the topological sense of the Eilenberg-MacLane space corresponding to G. So it turns out to be, on the one hand, I mod I squared, where I is, again, our friend, the augmentation ideal, which is definitely a thing. And on the other hand, it turns out to be just the abelianization of the group itself. So that, okay, if you believe enough things, then I guess you believe the last thing, right? Because the Eilenberg-MacLane space had fundamental group G, and so therefore the first homology group of a topological space should be the abelianization of its fundamental group, right? So that's consistent with the topology. And so yeah, I'm only going to take a few more minutes, but what's the idea here? The idea is that, again, I want to use my interpretation of group homology as Tor over the group ring. So this is Tor of Z over the group ring. And okay, so in this case, what's the point? I have this short exact sequence of Z modules coming from the augmentation homomorphism. And let me just apply Tor of blank comma Z to that. Okay. And let's see, yeah, so I only want Tor 1, I guess, is part of the point. So I just need like a little bit of a portion of my long exact homology sequence. So yeah, let's see. So right, what am I getting here? Right, so at the bottom, going from right to left, I should be taking the 0th cohomology of all these things, and the 0th cohomology is either the largest invariant quotient, which is given by tensoring from ZG to ZG mod I. So the largest invariant quotient is obtained by modding out by the image of the augmentation ideal. Okay, Z is trivial, so its covariants are Z. And again, here I'm going to use the interpretation where I tensor over the group ring to the group ring modulo I. But if I started with the group ring, then I just get ZG mod I, which is Z. Okay, and then here I'm tensoring I with ZG mod I. So I get I mod I squared, great, and then I get these tors. All right. So you look at these things, okay, and so you look at this exact sequence, yeah, and so you find let's see, why is this tor equal to 0? If it is equal to 0, then everything is great. Then this portion of the long exact sequence is just telling me that this tor1 is isomorphic to I mod I squared. Okay, so why is this equal to 0? Well, for what type of modules are do the tors vanish?
Is it supposed to be Z or ZG?
Where?
ZG. Is it supposed to be ZG Z or ZG ZG?
It is supposed to be ZGZ because I'm taking the long exact homology sequence here, right? So I go right to left. I get coinvariance, 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 connecting homomorphism, tor from. Wait, am I getting confused myself? Maybe I am. Hold on.
Is that the middle one?
Yeah, no. Oh, I see what you're saying. I'm sorry. This one is supposed to be ZZ. Yes. Is that what you're saying? Yeah.
Yeah.
Sorry about that. Good, correct. That's the thing I'm trying to compute. So we agree. Why is this one 0? Sorry about that. Yes, yes, that should be ZZ. So why is this one 0? This one is not 0. It's I mod I squared.
ZG is a free ZG module.
Yeah, hence projective.
Yeah.
Okay. Yeah. So projectives are acyclic for all right-derived, left-derived functors. Yeah. In fact, flat. It's a little bit better using properties of tor. Any flat module would be acyclic for tor, but this is a free module. Okay. So that's why this is 0. So great. And so the short exact sequence resolves. Sorry, the long exact homology sequence resolves, and it just gives us an isomorphism between this tor1 group that we agreed was h1g comma z. So h1g comma z is I mod I squared. And yeah, maybe it's a pretty elementary, just an elementary computation. Yeah, I don't want to go through this in detail, but I guess there's a map from G to I mod I squared where you just map G to G minus 1. Okay, and then there's another map from the additive group of I to GAB. Okay, and then I is generated by guys of the form G minus 1. And so you send that to the coset of G inside GAB. And again, it's not, I don't know that I'm ever going to use it again, so I don't want to talk about it in detail. But anyway, it's easy enough to write down two mutually inverse isomorphisms between GAB, the abelianization of G, and I mod I squared. Okay, so that's the second part of it. So it was just the usual homological formalism immediately shows us that tor1 ZZ is isomorphic to I mod I squared. Tor1 ZZ was also the first homology group, and therefore the first homology group is isomorphic to I mod I squared, which via this elementary argument you can see is the abelianization of G. Okay, so this was our first group homology computation, but it was a satisfying one if you believe what I was blathering on about the Eilenberg-MacLane space. Okay, I'll stop here. The next examples I'm going to do, I'm going to compute the homology and cohomology of an infinite cyclic group. And then I think I'm going to leave as an exercise the homology and cohomology of a finite cyclic group. And then the next, then we'll start talking about